Okay, good afternoon, everyone. Can you hear me?
Yep.
Okay, all right, thank you. So before we start the lecture, a couple of things. First, I've put these paper presentation schedule here, so you can check this Excel sheet and check the time and the paper you've been selected, so you can, prepare ahead. Okay, and also also extend the proposal deadline for like this Friday, because I noticed you have a paper due on tomorrow. So I just further pushed the deadline for the proposal 2 or 3 days after. So you have more time to prepare. Okay, but if you have some questions about this project proposal, feel free to let me know. We can, discuss, something or some issues you may have or some doubts you may have. Okay, and also please don't forget you also have this paper review deadline coming up. So please make sure you're able to submit the review report on time. Okay. Okay, so for today, we'll talk about medical image segmentation, which is very important topic in medical image computing. So for this lecture, we'll talk about the problem definition, right? What is medical image segmentation, and what are the common evaluation metrics we are using, when we do this medical image segmentation, and some of the, different various data set for different applications, right? For the lung, maybe for the heart, liver, and also different modalities, right? Like CT, MRI, etc. Okay, and we'll also briefly introduce several traditional methods. Then we'll go to the main part, which is the deep learning based method. Because right now, if you look at the recent, conference or journals, people have been shift the paradigm of using deep learning based approach for medical image segmentation because of the great success of deep learning techniques. Okay, so we'll go through a couple of mainstream deep learning based method for medical image segmentation. Okay, so for the semantic segmentation, this is very classic topic or research problem has been exist a long time ago in computer vision or image processing. Okay, so the goal of semantic segmentation is just trying to label each pixel in the image with a category of label, right? So if we are, talking about the natural image semantic segmentation, right? So maybe we have a photo we took, right? Maybe during a trip, we want to segment, if this is a human, this is a dog, a cat, right? Different categories. And we want to label each pixel, right? What the category this pixel belongs to, right? Maybe this is sky, this is grass, right? So as compared to image classification, semantic segmentation is a very dense prediction, right? Image classification is we just only one single label, for the entire image, right? But here, for the semantic segmentation, we want to, predict or assign a label for every pixel in the image. But also for the general semantic segmentation, we do not differentiate instance, right? We only care about the pixels. So there's also some other subcategories or topics under semantic segmentation that do care about different instance. But for here, the general—
You're breaking up the audio.
Can you hear me?
Yeah, it's clear, Professor.
Okay, so is there any issue with other student, the audio?
Audio sounds fine to me too, yes.
Okay. Okay, so for example, let's say there is an image, right? We have maybe in the image we have we have three cats, maybe 5 dogs, right? Maybe in a park. So for the general semantic segmentation, all these, 3 cats or 5 dogs, they all going to belong to the same category, those pixels. We don't have to distinguish different instances, right? This is dog 1, this is dog 2. We don't have to care about that. No matter how many dogs are there, how many cats are there, so all these pixels will belong to the same category, okay? So we don't differentiate instance, okay? But for some of the applications, for example, autonomous driving, right? We may have to differentiate some of the instance, or for example, other application like tracking, right? We tracking different object, right? We have multiple cars in the video, then we want to track individual cars, then we have to differentiate, each instance. But that's another topic. But for here, for the general semantic segmentation, we don't have to differentiate instance. Okay. So for medical image, the same thing, right? So it's just the image are different. So here, this is an example like MRI from the brain, right? So we were going to using image processing technique to analyze or process these 2D or 3D images to achieve segmentation, either maybe human organs, soft tissues, or maybe diseased bodies, right? Like a tumor. So here, this is an example of brain tumor, right? So these labels, different colors, right? Yellow, red, and green, they are indicating different tumor region. And because the medical image may have different modalities, right? X-ray may have 2D image, but for CT, MRI, those are 3D volumes, right? You have different slices, okay? Okay. So the process of medical image segmentation can be generally have the following step, right? The first is you want to obtain the medical image data set, right? What kind of application you are using, right? Are you interested in maybe brain tumor segmentation, or maybe you are doing some cardiovascular segmentation, right? Like the heart, different other vessels. And also, once you have the data set, as any common, image processing or computer vision applications, you want to do some pre-processing of these data or the images, right? The typical pre-processing step will be just normalize the data, right? Maybe resize the image to the same size in case, the image you are collected are not have the same resolution, right? Maybe you want to kind of resize those images to the same resolution. So it's going to be very easier for the machine learning algorithm to deal with. Also normalize the data, right? Like subtract the mean and standardize the image, right? So those are some very common practice, for machine learning or image processing. So once we do this kind of necessary pre-processing step of the image, then we'll try to select what's the appropriate medical image segmentation method, right? So so for later we'll talk about if you're interested using deep learning based method, right? You may want to think about what's the best network architecture you want to use for segment your particular medical image. And once we have the method, right, we using the model, and eventually we want to evaluate the performance, right? That is how good is your model perform on some of the testing data, okay? So we will talk about some of the evaluation metrics for this purpose. So there's several standard evaluation metrics for segmentation. So the first one is the called the DICE index or DICE score, which you will see a lot of papers they're using DICE score to measure the segmentation performance, right? You review the UNet. So the DICE score is a one common metric to measure the segmentation performance. And the definition is very simple, right? So here you have the cardinality of these two sets, right? A and B. A could be your prediction, right? B could is the ground truth, right? This basically count the number of elements in these two sets, right? And this is the intersection of these two sets, okay? And you have a scalar multiplied by 2. Okay, so visually, this is like one example, right? How much overlap is your prediction as compared to the ground truth, and you have these total elements of these two sets. So the dice score is going to be a scalar, right? And a value between 0 and 1. So the idea or the maximum score is 1, right? That your prediction is perfectly aligned with your ground truth, right? So you make the perfect segmentation, you will achieve a dice score of 1, okay? And also you have this Jacquard index, right? This is like the intersection of union that you will see on maybe the natural image semantic segmentation, right? This intersection of union is the very common metric to measure, to evaluate how accurate is your segmentation, right? So the idea is you have the intersection, right? And also you have the union, right? So this is your prediction, this is your ground truth, right? What's the union of your prediction and the ground truth, and how much is the intersection of your prediction and the ground truth? So that's the IOU metric. And also for the medical, this Hausdorff distance is also a very common metric that is being used along with dice score, right? So if you look at some papers, they not only report the dice index or dice score, they also report this Hausdorff distance. So the Hausdorff distance is the maximum distance of a set to the nearest point in the other set, right? So this could be your prediction, the green line, and the blue line could be your ground truth, right? So you basically measure what's the maximum distance from this prediction set to the nearest point in the other, in the other set, which is the ground truth. Okay, and the formal definition is here. Okay, so you can look at this equation, and this has some built-in functions. You just have to call this distance, and you are able to evaluate this metric. And for data set, we here I list kind of several of them, right? So we have different modalities, and we also have for different objects, right? So some of the data set, they contain images like MRI, CT, and they may targeting a specific body region, right? Brain, breast, liver, prostate, lung, etc. Right? So depending on what kind of applications you are interested in. So for example, maybe you are doing some final project, right? So if you are doing some application involves like liver tumor detection, right? Maybe this LITS data set is an option you can check out. Okay, so also list these website so you can check some of the details for these individual data set. And we can quickly go through a couple of very popular ones. So this brain tumor segmentation breadths. So that's for the brain tumor segmentation using MRI. Okay, so these are some of the examples here, right? So these different colors indicating different tumor regions, and the other part is going to be normal tissue. Okay, so they have a label 0. Also, we have this digital retinal image for vessel extraction, right? So basically, we want to extract this very narrow, thin vessels in the retinal image, okay? So this is a binary classification, right? So we have this white is considered the foreground, right? The vessel, and the other part is going to be the background, right? Which is the black region. And also this one is the for the 3D cardiovascular MRI, right? You want to do this kind of vessel segmentation, a different, part of your heart, right, left and right, and this different heart vessels segmentation. And this data set, KITS, 2019 and 2021, this is just indicating different years because they have this competition. So for this data set or challenge, they were aiming for kidney tumor segmentation using CT scans. Okay, so here are some of the examples here, right? So this is the this one view of the CT scan, and the green one indicating the kidney tumor. Okay. So those are some of the, just a very brief introduction of some of the very popular data set. And next we'll talk about some of the traditional method, before deep learning. So how people, are doing this kind of medical image segmentation. So we'll just look at several very classic methods for medical image segmentation. So the threshold-based method is very simple to use, right? So the basic idea is you consider the pixel intensity, right, itself, but without considering the spatial characteristics. So basically, if you have an image here, you can, based on the pixel intensity, right, you can plot this histogram. Okay, each being indicating how much pixels fall into this pixel intensity, right? So maybe I have a lot of pixels that fall into the region of maybe 50 to 100, right? You can see there's a peak right here, right? You may also see another peak, right, of the pixels may fall into 150 to 220-ish. Okay, this region, right? So these are the two majority of the pixel fall into these two. So here we can, for the threshold, you may think, okay, maybe 100, right? It's a decent threshold to separate, right? Because I can clearly see that, one class of pixels has the pixel intensity, below or smaller than 100, right? I also have another cluster of pixels, right? They are greater than the value of 100, right? If I using set a threshold, then I'm able to, separate these two classes very well. Okay, so for example, this image right here, right? So it's, visually you can see that, right? These coins are the foreground, right? And the background, which is this blackish, right? So we have very low intensity value, right? So we can using a single threshold to separate these two classes near perfectly, right? So maybe here is some misclassification, just a tiny bit, right? Maybe the edge is not perfect, but overall, we can see that this threshold, if you select properly, right, we are able to perfectly separate these two classes. So come to this medical image here, right? If we're using this threshold-based method, right, by plotting this histogram of the intensity or gray value of the image, we are able to maybe pick optimal threshold to separate the images, right? This brain image, okay. But yeah, one limitation of this threshold-based approach is that it is very sensitive to noise, right? So if you have some speckle noise, right, which may have some large values, that you can easily make a misclassification or segmentation. And also, because it does not consider some of the spatial characteristics, right? And you just look at the pixel value, right? You are not looking at some of the spatial structure information. So you may also have some of the misclassifications. Maybe the tissue, their intensive value can be different, but structurally or semantically, they belong to the same class. But if you base on the pixel intensity only, then maybe you'll make some misclassification there. Okay, so the robustness is not very high. We'll also have the edge detection based method, right? So for edge detection, it's also very, basic low level task, right? We want to detect the edge, right? We can using some of the edge detectors like the Kenny edge detector or Sobel edge detector to detect these edges, right? So then we maybe can using some of the algorithm to remove some of this kind of speckle noise, small part, right? So eventually you can generate a pretty decent edge map, right? Then you can use that to differentiate different classes. So that's the edge-based method. Also, we have this region-based method. So this watershed method. So for this watershed segmentation, so simply put, we can make a, to understand that, we can make an analogy is, you can think of an image as a surface, right? Where the bright pixel represent the mountaintops and the dark pixel will represent the valley, okay? And the surface is kind of punctured in some of the valleys and then slowly submerge into like a water bath. And the water will pour into the puncture and start to fill the valleys. However, the water from different punctures is not allowed to mix. So therefore the dams need to be built at the point of first contact, right? These dams can be, boundaries of the water basins and also the boundary of image object. So you're able to, build these kind of boundaries and segment different parts, okay? So if you're interested in this kind of classic approach, so this is the reference you can look into. And also we have this, segmentation method based on the graph theory, right? So basically we want to, using some of the, like for example, the graph cut approach, right? Using this to segment the image, okay? So those are some of the classic approach, right? So they all have some of the limitations. So, and most of them are based on some of the hand engineering or design principles. But since the deep learning become very successful in many computer vision applications, and medical imaging is also kind of adopt or shifted these kind of, computing paradigm to the classical method to this kind of deep learning based or data-driven approach. Okay, so here I list one survey paper that is for deep learning based method for image segmentation. So they kind of broadly categorize into this pixel-wise classification and end-to-end segmentation. So for this pixel-wise classification, basically you can treat the semantic segmentation as a classification task, right? You basically classify each pixel to one category, okay? So there's a very common way to do that. You can, for each pixel, right, you can take a small neighborhood, right? Consider maybe 5 by 5 small region, right? A 5 by 5 small region. And the goal is you want to classify the center pixel, okay? 5 by 5, the center pixel, what's the category, right? Because, semantic segmentation, we have to pay attention to the context, right? So that's why we select a very small neighbor, 5 by 5, in order to capture those contextual information. So you can make a good classification on the center pixel. Okay, so you can do this, for each pixel, right? At each pixel location, you select a small 5 by 5 neighbor patch, right? And go through the CNN and do the classification for that center pixel, right? You can do this, for every pixel and, make a prediction. So that's kind of pixel-wise classification. And we can also do the other, which is the mainstream approach, right? Here is the end-to-end segmentation. You can, basically we take the image, then we predict a segmentation map for the entire image. Rather, we do this kind of individually, one by one, right? You have a one input image. We do go through this end-to-end network. We output segmentation map has the same resolution as your input, okay? And here are some of the, have different architectures, right? And I even have some generated adversarial network-based approach for segmentation. So if you're interested, you're welcome to look at this survey paper and have a better view or general view of this medical image segmentation, what kind of method people are using right now. And this is a kind of another view, like using the tables to present, right? Different deep learning approach used for different data set or data modalities. Okay. Okay, so we'll go through a few very classic deep neural networks for this end-to-end segmentation, right? And we'll kind of dive into some of the details, like what's the motivation of designing such a network, right? If there's any limitations for a particular network, okay? So the first one is the fully convolutional network, okay? So you have this input image, right? So you go through this network, then you predict a segmentation map like this, okay? So let's understand how exactly this fully convolutional neural net works, right? So they basically adapt the network from the classification network, right? Before we have image classification, right? You have an input image, we generate, we go through this conv layer, we have a couple of fully connected layers, then you have this output layer, right? For ImageNet, you have 1,000 classes, right? So you make this kind of 1,000 way of prediction. Maybe this is a tabby cat, right? So now from classification, we want to adapt it to semantic segmentation, right? Not just one label for the entire image, but the label for all the pixels in this image, right? So what they do is they kind of convolutionize the last a couple of fully connected layer, right? And make it to output a heat map, okay? So here, this is one particular heat map, right? For tabby cat, this class, right? So how this is the basically the score for make a prediction of this tabby cat, okay? So if you have another class, right? I can generate, this network will generate another heat map. So you can generate, depending on how many classes you have for your semantic segmentation task, you can generate that many, heat maps, okay? So then we'll just take the maximum. For each pixel location, we'll just take the maximum value and, assign the label corresponding to that, the maximum value, okay? And based on this fully convolutional network idea, so later there's developed this UNet architecture for specifically designed for medical image segmentation, which you already reviewed, right? This UNet, very classic or maybe very well-known architecture in medical image computing, right? A lot of later improvement or advancement has been built upon this UNet. So we can, go through this detailed architecture and see what's some of the key innovations for this UNet. Okay, so as you can see from their, architecture diagram, right? So the shape of the architecture is like a U-shaped, right? Like an English letter U, right? So I think that's where their name U come from because of this architecture. And typically you will see there's when we talk about a UNet or semantic segmentation, you will heard there's an encoder and a decoder, okay? Encoder, which is the left part, right? We have conv layers, right? Then we have this pooling layer to reduce the spatial dimension, okay? Gradually reduce the spatial dimension, right? So we kind of build this kind of high-level representations, at different levels, right? And remember, the final output for semantic segmentation is a classification map that has the same size or same resolution as your original input, right? But because of the pooling, right, the feature map has been gradually reduced, right? Maybe here 1/8 of the original resolution. So we need to have some mechanism, right, to increase the spatial resolution so that eventually the output segmentation map has the same resolution as your input data, right? So that's the decoder part, right, which have the opposite of operation as pooling, right? That's the up convolution, right? Basically, this is increasing the feature map size, right? You can think about this is like a simple interpolation, right? Like a linear interpolation, right? Increase gradually, improve the resolution, maybe by double the resolution, right? Every time you can double resolution gradually to the original size. So this is considered as the decoder side, okay? So the encoder, you want to extract different levels of representation, and on the decoder side, right, you want to gradually increase the resolution, eventually, output a segmentation map. And one kind of innovative component in the UNet is this kind of, skip connection, right? You have this green arrow, okay, kind of bridge the information from the encoder to the decoder, okay? So let's see what this green arrow is actually doing, right? So for the encoder part, right, we have this conv layer, we do the pooling, right? And we reduce the size. And let's look at this particular layer here, okay? And at this point, we have this, this is 28 square of the feature map, right? And we do the upsampling, okay? So this is the, let's look at this blue part, right? The blue feature map here, right? So you can see there's a gray arrow here, right? So indicating I'm going to take, the encoder part, this layer of the feature map, and concatenate with this feature map I have in the decoder side, right? So basically we double the channel size, right? Originally we have 512, right? Because we injecting another 512 channels from the encoder. Right now we have 1024, okay? And for the next level, I do the upsampling here. Then I also take the corresponding encoder feature map from this layer, and I concatenate them in the channel dimension together to double the channel dimension from 256 to 512, right? So gradually you can do the go to the next level, do the same, okay? And you can easily see that this encoder decoder structure is symmetric, right? Say you have 3 pooling layers, right, to reduce the dimension. Then from my decoder, I also have 3 upsampling layer, right, to gradually upsample or increase the resolution of the feature map. Okay, so this is symmetric. Okay, so that's why you can using the corresponding layer of the feature map from the encoder in the decoder part. Okay. And the reason they are doing this kind of injecting some of the feature from encoder is they want to retain some of the good spatial information, right? If you think about, right, when the convolution layer goes, the network goes deeper, right? Because of this pooling operation, right, we lose a lot of spatial information. What we gain is some high-level representation, right? But the spatial information are kind of lost, right? When we go in deeper into the layers, right? And how can we bring those spatial information back, right? One way you can bring that information back is go back to the previous layer, right, in the encoder, and reuse that information in your decoder, okay? So that, in this decoder part, you are able to leverage some of the previously learned spatial information, right? So for this particular layer, right, I go to the previous encoder part, right, previous layer. I take some of the information from there, I inject in here, right, so that I can reuse some of the information I learned from the previous layer. Okay, and so the reason for this is, a lot of medical image, right, like the tumor, for some of the organ parts, they occupy a small region, right? So spatial information is very important, right? So by doing this, the segmentation outcome can be improved. And also another thing in that unit is called this kind of overlap tile strategy. Okay, I think if you pay attention to their network dimension, you may notice this, right? So look at their input tile dimension, right? The spatial one. It's 572 by 572, right? But for their output segmentation map, it's a smaller size, right? 388 by 388, right? As we mentioned, right? So segmentation map should have the same resolution as the input. Okay, so here what they do is they take the input is actually this blue tile, right? So this blue box highlighted tile, and the target segmentation region is this yellow box, right? The center, a smaller region. Okay, if we take the original, larger one, right? The edge information may lost, right? So a lot of medical image application, right? We care about the boundaries, right? So that's why they kind of leverage this kind of overlap tile strategy, right? Using a larger one to bring some of the context for this kind of segmentation boundaries. And once this part tile is segmented, then you can move to the next position, right? And of course, there are going to be some overlap. Then you can maybe take the average of them for the segmentation result. Okay. And this is the result for the unit. Okay. There's some dice scores and intersection of unit on this kind of cell track challenge. Okay. So the unit is actually a 2D convolutional neural network. Okay. And because a lot of medical image, they are dealing with 3D volumes, right? For example, MRI, CT, right? So you have multiple slices, right? Not just a single 2D image, right? You're actually dealing with multiple slices as a 2D volume. Okay, so then researchers kind of starting to think, okay, obviously you can still using 2D unit, right? And apply it to those 3D volumes, right? You can process them one slice at a time, right? Take the first slice, I apply 2D unit, get the segmentation, then I go to the next slice, apply the 2D unit, get the segmentation, right? But researchers started to think because of these scans, neighboring slices, they may have some correlations, right? Those tissues evolve over the space, right? Maybe tumor, some of the neighboring information can help you better understand the tumor region, right? Can we leverage some of the neighboring information, right? Maybe during the feature extraction part, right? I'm not only looking at a single slice, right? I want to look at multiple slices so that I can understand the context better to make a better prediction. So that's the 3D unit, right? They are using 3D convolutional kernel in order to operate multiple slices at a time, right? Not just looking at a single slice. Okay, and the architecture is still the same, right? You have this U-shaped structure, and you also have the skip connection, right, from the encoder to the decoder, right, at this same level of layers, because of symmetric architecture. The only difference is, from 2D convolution become the 3D convolution. So you're able to operate on multiple slices. And also, obviously, to work with 3D convolution, then you have 3D poolings and 3D upsampling, right? So here I want to see if I can annotate here. Okay. Yeah, please excuse my drawing here because I think this is quite difficult for me to draw this properly. So to save some time, I just draw this very simple feature maps here. So to help you understand what is this 3D convolution, how it's operate, right? What's the difference as compared to 2D, okay? So in this case, let's look at, let's see this. Okay. So for this one, this is individual slice. Okay, we have H and a W and a C. Somehow I cannot see the mouse. Okay. So this one is you can see you can consider this is a individual slice like MRI or CT scan. Okay, we have height and width, and also C indicating different modalities or channel dimension, right? For RGB, we have 3, right? R, G, and B. But for medical, for example, the MRI, we have T1, T2 flare, right? Remember, we'll talk about the MRI modality, right? So, and maybe T1 enhanced, right? So this is the different modalities can form these different channels, okay? So in this case, let's say we have 4 channels, okay? H, W, and 4. C indicating the channel dimension. And this is the different slices, okay? Let's say we have 100 slice. And so we're using D depth to indicating this is the slice dimension, okay? So for the, I think I have to quit this. Okay, are you able to see my screen now? Because I exit the present mode. So are you able to see?
Yeah.
Okay.
Yeah, Professor, we can see it.
Yeah, I can annotate here. So let's say we now have a 3D convolutional kernel, okay? So for 1D, right, for 2D case, right, you can make this disappear, right? Because we are operating on individual slice. But for the 3D convolutional kernel, the intention is that we want to leverage the information that is in different slices, right? Let's consider I have a 3 by 3 by 3, okay? Spatial 3 by 3, but also I have a depth that is 3, right? I take 3 slices at a time, right? So this convolutional kernel look at 3 slices, right? So in this position, right, I do this kind of element-wise multiplication. I generate a scalar, okay? So gonna be something here, right? I'm using this blue as a feature map, right? Okay, so if I move into the next position, right, I generate another pixel. Okay, if I do this, right, sliding window fashion to the end, I generate a feature map, which I draw here, like this blue one, okay? So now what I do is I shift, right, to the next position, okay? Looking at 2, 3, and 4 slice, right? I repeat the same, okay? Do the same, and I generate another blue feature map here, okay? So because we are operating on different slice dimension, right? Let's consider this is another slice, okay? So once we go through all these slides towards the end, right? So we generate this kind of 100 feature map. Let's consider them corresponding to 100 slices, okay? And this is just a single kernel, right? Then I can take another kernel of this red one, I repeat the same process, right? So from the beginning, right, I do this, then to the end, I generate this red, okay, this red feature map, right? One kernel generate one feature map, right? And this is corresponding to the first slice, okay? So if I do, incorporate more of these different filters, right? Maybe 200 filters has been applied, then each of the feature map will have 200 channels, okay? Then the depth still going to be 100, okay? So as you can see that compared to 2D, right? The 3D has the advantage of looking more in this kind of depth dimension, not just looking at the information within the single slice. I'm able to look at multiple slices. Of course, you can make this depths larger, right? Maybe you can, maybe 7 by 7, 10 by 10, etc., right? But remember, if you use a large kernel, the computation is also going to be increased, right? Because we have K by K by D, and also have the channel dimension, right? So that's how many parameters there is in this kind of 3D convolutional kernel. So we have a larger kernel size, then you have more computation. So that's actually one limitation of the 3D CNN neural network as compared to 2D. You have a significant increased computation. But the advantage is that you leverage more information during this kind of feature extraction part. And also you are not individually process this slice, right? You can actually take the 3D volume as input and generate the output, okay? So actually the output is going to be H, W, and a class. So you have a first slice, you end up with the prediction output gonna be H, W, and the number of classes. Let's say we have 5 classes. So your output first slice will be H, W, and 5. Then you have another output for the second slice, H, W, and 5, right? And how do you generate segmentation map? So basically for each pixel location here, I just take the arc max, right? What's the maximum value for this each pixel vector? And I will just take the corresponding class for the maximum value corresponding to the class for your output segmentation map. Okay. Yeah, but this is basically how 3D convolutional neural networks, and I hope you're able to capture, how it operates and what's the difference as compared to 2D. Okay, so yeah.
I had this question, but it's and it was in the beginning about the Hausdorff distance. Will you be answering that right now or like after the class?
You have a question?
Yeah, I have a question about the Hausdorff distance, like how that is working. Actually, I couldn't understand that. So
yeah, so the Hausdorff distance is just basically measure how far like two subsets of a metric space from each other. Okay, so basically you want to maximize these two, the distance of these two sets. Okay, so for the dice score, you want to maximize, right? Because that's involved the intersection over union, right? How much overlap is compared to the ground truth. But for the Hausdorff distance, right? Because like in the beginning, we have those two sets, like two lines, right? Blue and green, right? You want to minimize the distance between these two sets, right? So if you're close to the ground truth, then the distance is going to be minimized, right? So basically, these are just two different measures how close your prediction as compared to ground truth, right? For the dice, you want to maximize them, or for the Hausdorff distance, you want to minimize that. So that's the two metrics. Okay.
All right.
Okay.
That's all it. Thank you.
Okay. And the next network is called VNet, which is very close to 3D UNet. So again, VNet is a 3D network, right? So by here, you can see they kind of consider these kind of 3D volume. So the difference as compared to 3D network is they are using this kind of ResNet structure, right? If you look at these gray step connections, right, you have here input directly towards here, because these are the conv layers, right? So here you have a summation, right? So this is like, this is the residual connection. So this is the design they put in this VNet, but the overall is very similar to 3D UNet. Okay, so this is just some improvement over 3D UNet, but they are trying to distinguish them from the UNet, so that's why they draw this like into this kind of V shape and come up with this VNet name for it. And yeah, so this is the table kind of summarize their outcome. This is the dice, and this is the Hausdorff distance. And they also compare with some of the other, approach. Okay. And also there's many UNet variants. Here I just list one, kind of take the different skip connections to the extreme, like the nested UNet, right? This called this UNet plus, right? So here you can see that these encoder part, right, gradually reduce the resolution. Then this is the decoder part, right? They have the upsampling pass right here. So instead of just symmetrically, right? So here I directly connect to the corresponding layer in the decoder. I can also, increase the resolution, then have some intermediate or hidden layers in between, right? So I can essentially jump to any potential layers, right? Here I can go to this route and go here into maybe the last layer of the decoder. Okay, so it's kind of you have the freedom or have the information flow freely, right, to different layers. Okay, so that's their kind of very a little bit, feels like a little bit complicated design, but it's the improvement over UNet. And this is the result of UNet plus. Okay, so this is the ground truth and UNet, and this is their UNet plus outcome. So as compared to the original UNet, right? Definitely they are able to improve the segmentation map, right? For if you look at this one here, UNet is kind of miss this small region, right? But they were able to capture that small region, okay, because of the different layers of level of information is able to freely flow into different layers in the decoder. And quantitatively, this is their result. And this is the score they are using, the IOU score for this particular data set. And they also compare the model complexity, right, in terms of how many parameters are there for their network, okay? So for UNet, they have 7.76 millions of parameters. For the UNet plus, they didn't increase a lot, right? Only maybe 1.3 millions of parameters, but they were able to gain a substantial improvement in terms of IOU performance. Okay, so another very important variant is called the attention UNet. Okay, so the attention in UNet is a method to highlight the only relevant activations during. So let me. Okay, great. So attention is basically highlighting only relevant activations during the training, right? So that's kind of based on the definition of attention, right? We want to pay greater attention to only relevant regions, right? We want to suppress or kind of pay less attention or ignore some of the region which is not relevant or not useful, okay? And so they're using this soft attention, right? Basically, weighting different parts of the image. Okay, so relevant parts of the image will get larger weights and less relevant parts will get small weights. Okay, for example, I want to put more weights on the the tumor region, right? Kind of highlight or make the network pay more attention to those regions so I can make better segmentation. But for some of the background region, right, not the foreground, I want to pay less attention, right? Focus more on the foreground region. Okay, and also the weights are learnable, right? It's not like we hard code some of the weights, right? Or we have some prior knowledge and hard code the weights. It's actually learnable. You let the network to learn how much weight we have to put for individual or some of the different regions. Okay. So let's look at some of the details of this attention unit, right? So this is the vanilla unit structure, right? So encoder decoder structure. And this skip connection here is trying to combine some of the spatial information from the encoder, with the decoder part to retain some of the spatial information, as I discussed earlier. Okay, but this process brings along some of the poor feature representation from the initial layers, right? Although the initial layer is able to retain some of the a little better spatial information, but the quality of the feature is not very high because this is just some initial layer, right? Gradually, we build high-level representations, right? So maybe we need some, mechanism, right, to suppress some of the activation that may not be relevant, right? When we injecting these feature map, we want to selectively injecting the knowledge in the upsampling part. So that's why they are what they are aiming for, right? Build attention to selectively focus on the regions that are important, right? And suppress the regions are less relevant or less important. Okay, so that's the improvement or modifications this attention unit has been done to the unit structure. So let's look at how this attention has been applied. So so this is their view like a structure. Let's directly jump into this attention gate. Okay. So this attention gate is applied at the decoder level. So this is one particular attention gate, right? So it has two input or control signals going into that, right? Which corresponding here, right? So this is the G, and this is the feature map, right? So from the previous layer, right? So when we apply this attention, then we'll kind of select, right, where you want to pay attention to the previous feature map XL here. And for a close look, let's maybe apply using some of the concrete numbers so you are able to understand the process, okay? So let's say the G here in the decoder feature here, and X, right? This is I wanna use from my previous layer, right? Based on the dimension, you can see that the previous layer has a larger dimension, right? If we have this 2x2 by 2 pooling. And we can using 1-by-1 convolution, trying to match the dimension, right? And also using a stride of 2 to reduce dimension, because here we have a summation, right? When you do the element-wise summation, we have to make sure the dimension match, right? So here I'll take this, 1-by-1 convolution with a stride of 2 to reduce the dimension, so they are able to do the summation. So the summation, the purpose is that so aligned weights can get larger, right? So if the information from the previous layer get aligned with the current layer, the weights will get larger, right? Because you do the summation, okay? And then we'll go to this ReLU, this activation function, okay? And Then we're using a 1-by-1 filter convolution to reduce the dimension, the feature dimension into 1, okay? And also we are using this soft sigmoid, right? Because, by, attention, which means how relevant is each individual pixel or region, right? We want to using a scalar to indicating that or highlight that. So we're using this sigmoid to map any value between 0 and 1, okay? 1 being very important, right? So we want to preserve all the energy instead of multiply with a smaller scalar to suppress that pixel, specific pixel, right? So that's why we're using this sigmoid function to map into a scalar between 0 and 1. And later we can, reshape and upsample it to the original size, right? Because here we have this multiplication, right? We take the original feature map and multiply with this kind of attention map, or you can call this importance map, right? Each value indicating how important is this pixel, right? So we do this upsample to the original size, right, which is 128 by 128, and we multiply with these original feature map. So this is kind of scales the vector, right, based on the relevance. So by do this kind of multiplication, the important region get highlighted, right? But from the less relevant region, they may have a very small value. It kind of suppressed, right? Because you make the value become smaller, kind of suppress those unrelevant region. So then you can, the rest gonna be the similar to the unit flow, okay? So that's the attention gate, how these function to kind of measure or weight different regions based on the relevance. And because these weights are learnable, right? So this is based on the objective. So eventually these weights are learned to be optimal to weighting different regions. And this is the visual representation, right? How this attention evolve over the training process. Okay, so these are like different attention map, right, across different training epochs, right, 3, 6 to 150. Okay, so this is the attention map overlaid on this original image, right? Towards once the model towards the end, right, maybe 150 training epochs, right, the attention map is become better and better, right? Eventually, it learns to focus on this particular tumor region, right? This pancreas tumor region, right here. You also focus on these very narrow regions, right? Instead of in the beginning, right? Maybe you don't know where to pay attention to, so you have this kind of large attention map, kind of pay attention to all different regions. But after the learning, you are gradually able to focus on some of the particular region that has these kind of diseased bodies, okay? And this is the segmentation map as a comparison to the original unit, right? So the blue one is the ground truth. Okay, so A is the ground truth for the pancreas, and this blue one just an enlarged version, right? Just enlarge this portion. And the red one is the segmentation map for the unit, and the green one is the attention unit segmentation map. So this red arrow indicating some of the regions or portions that attention unit did a better job than the unit, right? As compared to ground truth here. And also this one is show the quantitative result in terms of the DICE score, right? So attention unit achieves better, DICE score as compared to the original unit. So those are using the attention in the unit. Just take recently transformer, which are very popular, right? It originally come from the natural language processing. Now people are using transformer in the vision domain, right? Trying to model those global or long-term relationship. So this is one paper called a transunit, right? They basically take some of the transformer layers and they incorporate or injecting them into the CNN layers. And hopefully this transformer layer is able to learn better correlation or long-range correlation across the image. So if you don't know vision transformer, here is just a very high level or simple visual representation. So how these transformer has been applied to vision problems. So for this one, we are dealing with image classification, right? So in the beginning, we are partitioning each image into small patches, right here, the 9 patches. Then each patch will be used as input, right? Individual patch. We could do using individual pixels, but it will make this computation intractable, right? If we have a high resolution 4K images, you can imagine how many input we are here and go through this entire network. So we are just, for the sake of computation efficiency, we using patch as a unit, a small patch as a unit. So each patch will go through this kind of feature linear projection, right? You can think of this as just, vectorize this small patch into a large, vector. And we use some of the position embedding along with the feature embedding, right? This, the purple one, right? Indicating, because we kind of, when we divide them into patch and put them as input, we kind of disorder the spatial correlation, right? But for image classification, the spatial relationship is very important, right? So we want to inject in some of the knowledge to learn this kind of spatial correlation. So we're using this learnable position embedding here. And then we go through this transformer encoder, right? Which is on this right part, right? Basically, we have some normalization layer, and we also have this multi-head attention. And this is basically using self-attention, has multiple self-attention head to learn those correlations. And then obviously we can using some of the good practice, right? The skip connections here. And then we go to another normalization layer normalization, and go to this MLP. So that's the structure of a transformer layer. Okay, eventually then we can make this prediction, right? Just like the CNN, right? So what's the, we have the prediction of the output, right? Probability of each class. Okay, so basically, people working on the vision problem want to leverage the design of the transformer, right? This kind of multi-head attention, and see how this is able to help learn better correlations in this image, right? Because in the segmentation, right, maybe some of the tissues or tumors happen, appear here, but also the same type of tumor maybe appear here, right? So we want to learn some of the long distance or relationship or global relationship better. So people want to using transformer, along with this CNN kind of like hybrid architecture. So this work, the trans-BTS, that is apply these transformer layer in the 3D CNN network. Okay, so the trans unit before you see that's a 2D network, but here we can also using the transformer in the 3D CNN network. So that's what they did, right? So you have this, still have the encoder decoder structure, right? You have the 3D CNN to do the encoding, right? Downsampling pass. You have the skip connection, injecting the previous, encoder features. But in between, in the middle, you have this transformer layer to model those long distance relationship before you go through this decoder part. Okay. Just put them side by side, right? So a couple of main difference is the trans unit. It's a 2D approach, right? You do this segmentation slice by slice. But for this trans-BTS approach, it's a 3D network, right? You take the original 3D volume you can do this in one go, right? You don't have to do this, do the segmentation slice by slice. Okay, you can take the 3D module and make this prediction for all the slices. Okay, and also for this transunit work, they're using pre-trained model, like pre-trained transformer network on some natural images, right? Like ImageNet, they are using this pre-trained model, but for this trans-BTS, they train from scratch, just directly train on this brain tumor data set. Okay. And this is another segmentation that using the transformer. It's just some of the small changes on how you apply transformers. Okay, so actually there's more. Also, they have some attention. Okay, they have some attention. They're using the attention unit rather just the vanilla unit. So these are some of the recent work. People have kind of trying to explore transformers in the existing CNN architectures, right? How you can incorporate a transformer into the CNN, combine CNN to make better performance. But now people may pay attention to maybe using the pure transformer network instead of this kind of hybrid, right? Using CNN plus transformer. They want to using a uniform framework, just the pure transformer to make this predict semantic segmentation. Okay. Okay, so that's all for the image segmentation. So basically, I think UNet still is considered like the predominant architectures being used in medical segmentation. The reason UNet is so popular or very successful is the design is quite simple, right? So there's no very complicated design in the network. Obviously, later, improvement, the people putting more complex structure like attention, some other improvement like UNet++, right? Different routing paths. But UNet itself is also able to work pretty well, I would say, for medical image segmentation. And, also you have to think about for your application, do you have to use very complicated or maybe over parameterized network, right? So UNet is very clean, simple. It works well for the medical image is because some of the medical image data is very small, right? So if you throw in very complicated design, over parameterize your network, that may make your model learning difficult, right? You have high risk of overfitting, right? So that's some of the trade-off or some things you have to think about when you dealing with your own application. Look at your data set at hand, right? Do I have to using very complex model or maybe a single unit, the vanilla unit will be sufficient. So yeah, so that's just some side note I want to mention here. Okay. Any questions? Kyle, what's your question here? I feel like this would be worse for the data set that are highly imbalanced. Which method this will be highly?
I was talking about the attention unit.
Attention unit will be worse for the data set are highly imbalanced. What's your thoughts on that? Why do you think it will be worse on imbalanced data set?
I guess perhaps I still don't understand it fully, but it seems like you're teaching it to only focus on one area more than others. So my kind of, I guess, naive thought would be it wouldn't generalize well and therefore perform worse with imbalanced data sets. But yeah, I don't know.
yeah. So I kind of understand where you're coming from. Maybe if it's imbalanced, right, you have some attention, maybe your attention is focused more on the majority of the class somehow, right? You miss some of the minority class, right? Maybe make that class learn even worse. Yeah, that might be the case, but I think in general, the imbalanced distribution is a common issue that may also affect the performance of attention unit. But I think you are bringing in a very good question, this kind of imbalanced problem. And that is also very true for many medical images, right, for the tumor. Some of the small tumor regions occupy a very small region. So that's the data distribution is highly screwed. So one way to address that is using the weighted dice loss. Okay, so actually this is a very common useful technique that called the weighted dice loss. How do you weight the loss? Is if you have a minority class, okay, which means you have less samples as compared to other classes, right? When you in this batch of the data, right? So when you compute the loss, right, you can assign a large weight for this minority class, right? You can, based on the statistics of your batch, right? Maybe class 1 only occupy 10% in this batch of data, and maybe class 2 occupy 70%, right? So what you can do is you can assign weights inversely proportional to the data distribution, right? So if my minority only occupy 10%, then when I compute the loss for these classes, I want to put a large weights on my loss, right? So that I emphasize this particular class, right? And for majority class, then I put a less weight on the loss, okay? Because I have a lot of class in this batch, okay? I don't want this class dominate, the loss dominate here. So I assign a small weights to individual, each sample for this class. So overall, even though you have a lot of these samples, but accumulatively, your overall loss wouldn't dominate the loss for the other class. Okay, so that's the weighted dice loss, which is a very simple strategy. You can treat this imbalanced sample. Another way is you can think about from the sampling perspective, right? When you process a batch of image, right? Maybe you can do some resampling strategy, right? Oversample the imbalance of the minority class. Or the other way around is you downsample the majority of the class, right? Intentionally, downsample those majority of class, or intentionally oversample the minority of the class. Okay, so that's from the sampling perspective. Also, you can address this issue from the data augmentation perspective, right? On top of my head, one way to do this is, for example, for medical image segmentation, for the training data, you have the ground truth, right? So you have maybe one tumor occupy a tiny region, maybe 10 pixels, how you can augment the data to make them represent more, right? To make the distribution more balanced. The simple way is maybe you can do copy paste, right? You take those maybe minority class, right, those 10 pixels, and copy that into other, maybe regions. Okay, you copy that, into random regions here. You can do this for the ground truth as well, right? How you copy to which location, then you can generate the corresponding, segmentation map. And hopefully this will kind of mitigate some of the imbalance issue. But again, this kind of very simple copy paste, there is a risk. Maybe there's some physical meanings there. Maybe one type of tumor supposed to within another type of tumor, like the brain tumor, some of the like enhanced core is going to be within the tumor core region. But if you just randomly copy to different positions, then some of the physical meaning of this kind of pathology will be changed, right? Maybe confuse the model somehow. Okay, so those are some of the things you can think about, right? Data augmentation, sampling strategy, and also do something in terms of the loss, right? Using the weighted dice. So those are some of the common strategies you can think of. Okay.
Yeah, thank you. That was a comprehensive
Yeah.
answer.
Yeah. Okay. All right. So any other questions? Okay. If you don't have any questions, we're gonna stop here, and I'll talk to you on Thursday. Okay. All right. Bye, everyone.
Thank you, Professor.
Thank you.